So we've already had a little sneak peek at the quantum computing room. We did an ad hoc walk around at the start of the conference. I'm now going to pass over to IBM's quantum computing guru, Adam Hammond, who's going to talk to us about the future of cybercrime and how quantum computing has a role to play within that. It's a session I'm really excited for. I think it's a real eye-opener. So coming to us from the room next door, Adam, over to you.
Hi, my name's Adam Hammond and I work within the quantum team here at IBM. You've just heard from Tone in the video that you saw before me the importance that encryption plays in protecting your data. And cryptography is the science behind encryption. And our digital world depends on cryptography and encryption to keep it safe. Whether that be online banking, online shopping, exchanging of credit card information, using your digital identities in order to be able to prove who you are to online systems. Now, we know in today's current computer environment that there are a set of problems that we know how to solve with today's computers. We also know that there are a whole set of problems out there that we can't solve with today's computers. And cracking encryption is one of those problems that we cannot solve today with today's classical computers. But the latest emerging technology that we're seeing is the science and technology around quantum computing. And the purpose of quantum computing is to give us a different way of attacking some of the problems that we can't solve today, or even attacking some of the problems that we can solve, but finding better ways of solving those problems. Examples could include, can we find ways of simulating molecules so that we understand exactly how they're going to react with different molecules? Can we find materials that have properties that we would like to see, whether that be extreme resilience, whether that be being waterproof, whether that be the way they interact or don't interact with other materials? Can we simulate those and actually create those? Can we find better ways of doing machine learning? There's already growing evidence that using quantum computing to build machine learning data models brings us greater insight. And there are a whole series of problems around optimization in things like costing financial instruments, network optimization, routing optimization, where we think that quantum computing will be able to give us better answers, more accurate answers than classical computing today. And this is all down to the fact that what quantum computers allow us to do is to simulate quantum mechanics. And quantum mechanics are how the world works at a molecular and atomic level. And up until now, all we've been able to do is very, very roughly approximate the way that the world works. With quantum computers, we'll be able to simulate the way that the world works much more accurately, and that will give us the opportunity to solve problems that are much more real world than we've been able to do up to now. The other thing that quantum computers allows us to do is it allows us to solve some really complicated mathematical problems much more easily. And one of those problems is the mathematical problem of factoring very, very large numbers. Let me give you an example. Today, if we wanted to find the prime factors of a 2048-bit integer, so two numbers, or a series of set of two numbers, the compute time to do that with the most powerful computer today is estimated to be millions of years. Now, why is this important? This is important because this is what sits behind the way that today's cryptography works. Today's safe cryptography relies on the fact that we use exceptionally big numbers that today's computers can't factorize in order to create our public keys without being able to factorize, which would give us what the private keys are associated with those public keys. So today we know that it would take millions of years to be able to crack a 2048-bit number, which means that the cryptography we're using is safe today. But with the advent of scalable quantum computers, we believe that using an algorithm called Shor's algorithm, this task becomes a matter of hours. What this means is today's cryptography will be cracked at some point in the future by the upcoming quantum computing technology. So where you've got public key encryption, where you've got digital signatures that rely on public keys and private keys, where you're exchanging these keys, we know that those schemas that are listed on the slide will be cracked by Shor's algorithm, potentially in a matter of hours. There's also another class of cryptography that we use, typically symmetric, where you're sharing, where you're hashing, where you're doing password derivation, that we know that a different algorithm will mean that they have to be improved. So we won't crack that, but it means that you will have to use larger key lengths, larger digest lengths. Now, the reality is we don't have a scalable, fault-tolerant quantum computer today. So why is this a problem today? So let's look at the data that potentially is encrypted today. So, first of all, let's look at our infrastructure. Simplest bit of infrastructure, if you think about our passports. Our passports all have a digital identity for us encrypted on a chip in the passport. We carry it around with us. Our passports generally are valid for 10 years. We'll be carrying that passport around with us for 10 years. Software in cars. How long does a car last? 15 years, 25 years? Trains, planes, probably longer, 25 years, 35 years. And actually we know that there are some mainframe applications that have been running for the last 50 years. But that's just the infrastructure. Let's look at the validity of the data that we may be encrypting today. You know, if you look at health data, the HIPAA Act in the US says 5 years. Tax records, we know in the UK that we have to keep tax records for 7 years. If you're doing clinical trials, that data has to be kept safe for 25 years. And in Japan, medical records have to be kept secure for 100 years. So where does that sit in terms of where we think we're going with quantum computers and potentially the ability to decrypt, to crack that data? So if we go to the National Institute of Standards and Technology in the US, who are driving all of the focus around quantum safe cryptography, their view is that it may be possible to break the current RSA key approach by 2030. That's less than 10 years away. If you talk to the Institute of Quantum Computing at the University of Waterloo, who are very focused on this and a leading research organisation in quantum computing, as you will see, by 2026 they think there's a 1 in 7 chance. That's less than 4 years away. And they reckon there's a 50% chance in less than 10 years. Gartner has a different view on the importance of doing this. And that is that what they found is that organisations that have taken this seriously and that are putting in place measures to become quantum safe are actually becoming safer overall. And they're 60% less likely to have security break-ins based around cryptographic issues, i.e. someone's cracked into their cryptography. So the reality is there is data out there today in all of your organisations which will still be valid and important and need to be kept secure within the timescales when there will be hardware, probably, to be able to crack it. What that means is that a bad actor could steal data from you today, and while they may not be able to do anything with it today, at some point in the future, at some point within the lifetime when the data that they've stolen is still valid, they will be able to do something with it. So what does that actually mean? What that means is, clearly there's a loss of data confidentiality. Clearly there's the ability at some point in the future, if they steal data from you today, that they will be able to read that data. They will be able to access the confidential information that you're storing in that data. But don't forget that this cryptography is used in other areas. It's used to define who you are. It's used in digital identities. So at some point in the future, it may be that somebody approaches and tries to get into a system using a digital identity that still looks absolutely valid, but because they've managed to crack the cryptography behind that digital identity, they're not who they say they are. We're also seeing increasing uses of digital signatures to prove that documents are valid, to maintain legal histories. And you can imagine at some point in the future, those digital signatures may not provide the assurance that we think that they do today. And that's why it's really important to think about this today before it becomes an issue in the future. Because data that people take today will be crackable in the future. Now, is there an answer? The answer is yes, there is. And for those of you that are interested in this subject area, you may have seen that NIST in the US published the finalists of a competition that they've been running since 2015 to find cryptographic algorithms that will still be secure in the face of both conventional and quantum computing. And there are 4 finalists. I'm delighted that IBM submitted 3 of the finalists. And while these move on the route to become standards, these are the recommended approaches to become quantum safe. These algorithms will not be crackable. They're designed in a way that they're not crackable by a quantum computer. And IBM's been on this route since 2016. We submitted these algorithms to NIST in 2016, but we haven't been sitting there doing nothing since then. In 2019, we announced our quantum safe tape units using one of the algorithm that's the final, dilithium. We have put quantum secure algorithms on the cloud and made them available to all of our customers. And of course, with the announcement of the Z16 mainframe this year, we have built-in hardware encryption based around the quantum safe algorithms. Does this mean that if you run your software on a Z16 that you're safe? No, of course it doesn't, because that's just one element of the architecture. The data moves around. So it's really important to be quantum safe that you understand the use of cryptography within your architecture, within your organization. You have to understand the threat. You have to understand what the potential attack vectors are, and you need to understand the risk. If you've got data in your environment that you know will be worthless in 5 years' time, probably not worth worrying about it. If you've got data that you know will still be valid and still have value in 15 years' time, well, that's a good example of where you might want to do something. If you've got a system that you're going to decommission in 5 years, again, maybe you don't want to think about that. But if you're investing in an infrastructure transformation that's going to last you the next 10 years, then quite possibly you do want to think about how you do that in a way that is quantum safe. I think what we all know is that we don't know what the threats that have not yet happened are going to be like. So it's not just a matter of redesigning it for a one-off threat, like, for example, we may have done for Y2K. We know that these cryptographic algorithms are going to get broken. We know that they may not be as safe as we think they are. We may know that some of the implementations might have bugs in them. And therefore, what we also have to be able to do is we have to be agile in the way that we deploy crypto into our environments, in the same way that we're agile in the way that we deploy software into our environments using DevOps. So crypto agility is a really important part of how we actually move forward. And then, of course, having crypto agility and understanding what the algorithms and the risks are all very well, but then you actually have to implement them. And this is all built on the need for better governance of how you manage cryptography within the organisation, in the same way that you may govern the way that you have software and govern the way that you may do security and access. Thinking about better ways of consuming cryptography. An awful lot of cryptography is hard-coded into environments. And then, of course, it's about automation, because when you start to look at the amount of cryptography you might have in your environment, everything from the certificates that you use to secure websites through to the way that you might secure stuff on a tape library, you need to be able to automate that, because if you're going to be able to deploy multiple crypto algorithms as they come out, you're going to need to be able to do that in a way that doesn't require a lot of manual effort along the way. So this is all about building agility in across all of these phases. So in terms of migrating to being quantum safe, the first thing you have to do is actually understand what data you have. You have to be able to classify it. You have to decide which data you need to think about when you're doing this. You need to do an inventory. And the inventory isn't just about what data you have or what systems you have and where the crypto is. It's about the dependencies. It's about how data moves from one area to another. So it's like building if you like, a crypto bill of materials of how your environment works. You then need to think about how you are going to be agile with your crypto. We've all seen vulnerabilities announced in our existing software. So this isn't just about being quantum safe, this is about how do you manage when the existing crypto libraries that you're using to do encryption are found to have a bug or found to have a vulnerability. So how do you update it when it's broken? How do you change it? Regulation might require that you use a particular type of crypto. That's probably going to happen a lot over the next few years as regulated industries move to compulsory quantum safe cryptography. But also, as new threats become aware, you may need to deploy new kinds of cryptography. You need to monitor when it's being used. You need to make sure that it's being used when it needs to be used. How many times have we seen people cracking data and that data is actually being stored in plain text and readable to the human eye? And lastly, you need to be able to decide when a particular crypto algorithm has reached end of life, and you need to be able to retire it. And you need to be able to do all of this without a significant amount of work effort. And what that does is that gives you quantum safe. So here in IBM, we have developed a quantum safe methodology that we think helps clients prepare to go on their quantum safe journey. And it's all about helping them inventory what they have, help them decide what needs to be done, and how to prioritize where they should focus first. And as I said, remember, being crypto agile isn't just about deploying quantum safe algorithms, it's about being able to respond to threats as they come in and being able to deploy new capabilities as they become available. So let me leave you with three thoughts. The first thought is that while scalable, reliable, quantum computers might be some time off, the data that those computers can be used to hack is around today and can be stolen today. The second thing is that being agile with your ability to update and upgrade your cryptography is the key to remaining safe. And that's actually true whether you're thinking about quantum safe or just today safe. So what would I advise? I would advise everyone to start thinking about how to protect yourself against current and future data breaches, and the ability in the future for bad actors to be able to get into the data and the digital certificates that you're using. Because I can guarantee somewhere in the world today there are bad actors stealing data and stealing certificates that they know that at some point in the future they will be able to get in and use for nefarious purposes. I hope that's been a useful session. Thank you for your time and have a great rest of the conference.
Hello, I'm Adam Robinson from IBM, and I'd like to talk to you about immutability. You've probably heard the word, and it seems like everyone is talking about it at the minute. We talk about it a lot at IBM, and I know when it comes to some of our competitors in the backup space, they also talk about it a lot. But what does it mean? Is it really so important, or is it just another buzzword? Immutability is actually a really straightforward concept. It essentially means when something is written, it can't be deleted or altered. It's permanent. In a world where ransomware sneaks into your IT environment and remains undetected for many months before being activated, immutability can be a very powerful tool, and definitely one that every enterprise infrastructure team should implement. You see, once that ransomware is in your environment, it spreads silently, far and wide. It will even be ingested into your backups. So when it's activated, it's going to cause maximum damage. It will start encrypting or even deleting your data everywhere, including your backup copies. Not all backup software provides true immutability, but with truly immutable backup copies, like you get with Spectrum Protect Suite, once they're written, they can't be changed or deleted. You will always be able to bring a copy back in its original state. It will always be there, whether you like it or not.